Okay, guys, so we're going to cover two things today, and I want to sort of tee them up with you by relating them back to what we talked about last time. So guys, last time, as we just got done grading homework, we've been talking about voltaic cells. Now, one of the questions that came up, and Jonathan sort of alluded to this, was how do we know which one's the cathode and how do we know which one's the anode? And guys, we had a short conversation about this where we said because this is a reduction potential chart and because reduction happens at the cathode, looking at the ones on the left, the one that is the highest will be the one that's more likely reduced and therefore the cathode, right? Okay. What we're going to do is we're going to take that idea and we're going to expand upon it, and we are going to have a pretty wacky little conversation about who can oxidize and who can reduce whom. We're going to talk about agency. Remember the very first day of this unit when I talked with you about agency? And we said an oxidizing agent does what? Oxidizes the other guy, right? So what does it mean that this guy over here is oxidized? What's it doing? Losing electrons. So what is the oxidizing agent doing if it's oxidizing this guy? It's being reduced, so it's gaining electrons. And conversely, a reducing agent is the guy that causes reduction in the other one. So if we're causing reduction in the other one, then this guy's losing electrons and being oxidized. Remember that? Okay, we're going to talk about that. Then we're going to call time out, and we are going to talk about spontaneity. You may remember that we said that when we pick the cathode and the anode, we always do it so that the voltage is positive, telling us what about the battery? That it works. It's spontaneous. But guys, understand that this oxidation reduction stuff doesn't have to just be a battery, and if it's not just with batteries, which we always write in the spontaneous direction, we can then use voltages to predict spontaneity. Positive voltages are spontaneous. What if the voltage is negative? Can that reaction be spontaneous? Yeah, in the other direction. Remember that? Now guys, make the connection. You now understand that voltage can predict spontaneity, but up until now, what was the only guaranteed predictor that you had of spontaneity? Gibbs free energy. Which Gibbs free energy values did we know for sure were spontaneous? Negative Gibbs free energy values. So now you got two. Negative Gibbs free energy values are spontaneous. What voltages are spontaneous? Positive voltages, and guess what we're going to do? We're going to bring those two ideas together in another equation that allows us to relate spontaneity due to voltage and spontaneity due to Gibbs free energy change. Won't that be fun? Here we go. So guys, step number one, you ready? Redox agents. Grab the brightest, boldest thing you got, and here's what you're going to do. Take your table, and guys, you are going to break your table into quadrants. Your horizontal line will pass through the hydrogen half cell. Why there? It's our point of reference. It's our 0 point. And then, guys, your other line will pass through the yield arrow, separating the reactants from the products. You guys got it? Okay, so guys, let me make sure that you understand the conversation that we're about to have, because this gets a little heady. You ready? What we are going to do is we are now going to learn to identify what substances are good at causing oxidation, what substances are not as good at causing oxidation, what substances are good at causing reduction and which substances are not as good at causing reduction. Now, along the way, we need to talk about some of the little nuances of this. But guys, here's the way we're going to have this conversation. In order to do this, and again, what we're doing is we're identifying weak and strong oxidizing and reducing agents. We're going to use our table as a guide. Now guys, in order for you to be successful with this, you need to remember that this is a reduction table. Which means, and guys, you may want to write this, not this, but write the thought down. Guys, this is a reduction table, which means that it is a table that measures the ability of these substances to be reduced, right? But if these are the substances that are being reduced, what are they doing to the other guy? Oxidizing them. So this is actually a table of oxidizing agent strength. I'm going to pause and let you wrestle with that in your brain until you can figure out that that makes sense. So guys, this is a table of oxidizing agent strength. And if you don't really conceptually understand why that's the case, and you're just content to blindly write it down, there's a very real chance that all the logic that goes into the conversation that we're about to have could be lost. So guys, let's say it again. This is a reduction potential chart, which means the ability of the elements on the left to take in electrons. But if these elements are taking in electrons, what are they doing to the other guy? They are oxidizing them because they're pulling electrons off of them. So if you're measuring the ability of something to be reduced, what you're really measuring is the ability of that something to oxidize something else. You get the idea? Okay. You need to talk about it. No, Taylor, heads up. I know that you're mourning the loss of your backpack, but hang in there. All right. So guys, don't write this down, but let me show you what we've got. We are going to talk about this then in terms of being a system of quadrants. And the way this conversation is going to go is on the left-hand side, we're going to have the sides of the equations left and right. Then we're going to have reduction values. And guys, the reduction values in your chart, right, are actually over on the right. Don't let this throw you off. But we're going to talk about values that are high, meaning positive, and values that are low, meaning negative. Okay? All right, so here we go. We are going to start in the upper left-hand quadrant. Okay, what is true? Well, first of all, what substances are we looking at? Are we looking at fluorine or fluoride if we're in the upper left quadrant? Fluorine. Are we looking at cobalt 3 plus or cobalt 2 plus? You get the idea? We're looking on the left. Okay, so with that said, these are the substances with high reduction potentials. So if they have high reduction potentials, what does that mean they're going to be very good at doing to other things? Oxidizing them. So guys, these are your strong oxidizing agents. I would write that down in this white space. These are your strong oxidizing agents. Now guys, let's talk. Why? Let's just talk about the extreme. Fluorine, F2. If we talk about extremes, the other things are just lesser examples of the same concept. Why is fluorine a kick, stinking butt oxidizing agent? Yeah. Good heavens. Not just a high, the highest, right? Guys, think about fluorine atoms. How many valence electrons do they have? 7. Their electronegativity is maximum. So what do fluorine atoms want to do? They want to take in electrons like stinking crazy. And when they do, what do they do to the other guy? They oxidize them. And guys, that's what it is that makes these things really good oxidizing agents, is they have relatively high electronegativities. They have places to put electrons, and so consequently they pull in these electrons, and they are good oxidizing agents. Does that make sense? So again, what is it that makes a good oxidizing agent? They have high electronegativities, and they have room to put electrons. Good? Yeah. We'll talk in a minute. I don't want to go there yet because it's going to blow people's minds. Okay? All right, guys. So that is this quadrant here, right? So now go down here. If these are the strong oxidizing agents, what will these be?
The strong reducing.
Which one is it? Well, guys, let's go with Ben's thought first, frankly, because he's wrong. But let's talk about why he's wrong. Ben's guess was strong reducing agent. Guys, think about this. In order to be a reducing agent, what do these elements have to do? Give away electrons, right? If they are reducing agents, they're giving away electrons. Why can't these things be reducing agents? They're all positively charged, which means what? They ain't got any stinking valence electrons to give away because they've already been given away. Do you get it? So guys, look. All of these things have positive charges. That means they are already missing electrons. Most of the time, they're missing all of their valence electrons. Now, guys, in order to be a reducing agent, remember causing a reduction in the other guy, you got to be able to give away electrons. And these don't have any valence electrons to give away. Do you get it? So can these be reducing agents? No, they don't have any electrons to give away. But guess what they do have? They have space to take in electrons, which makes them what? Oxidizing agents. But guys, they're not very good at it. Why not? Their electronegativities are relatively low. So guys, down in the lower left-hand quadrant, we have our weak oxidizing agents. And guys, please don't screw this up. A weak oxidizing agent is not a strong reducing agent. These guys can't reduce anybody because they ain't got any electrons to give away in the first place. We know that because of their positive charges. You get the idea? Okay, so now let's go to where Matt was going. You ready? Upper right-hand quadrant. Now we're looking at the guys on the right. Let's again look at the extreme example, fluoride ion. Can fluoride ion take in electrons? No, it's full. So if fluoride ion cannot take in electrons, what can't it be? An oxidizing agent, right? It's got nowhere to put electrons. If fluoride wanted to go, hey, I'm going to oxidize you, it couldn't because it can't take in electrons because it's already full. So guys, if fluoride can't take in electrons because it's full, therefore it can't be an oxidizing agent, what can it do? Give away electrons, making it what? A reducing agent. But how likely is it going to be that you're going to get fluoride ion to give away electrons? Pretty stinking close to zero. What do we call that, by the way? The amount of energy it takes to take away an electron. Ionization energy. Because these have freakishly high ionization energies. So the bottom line is this. Fluoride ion cannot take in electrons, so it can't be an oxidizing agent. So it has to be a reducing agent. It could give away electrons because it has extras, but it doesn't do that very readily because it's so stinking strong. So what would that make these? Weak reducing agents. Now, guys, down here in the bottom right-hand corner, let's go to the other extreme and let's talk about lithium. Can lithium take in electrons? No. It's got an electronegativity of like 0.1. Poor little fella. So, guys, lithium doesn't have a whole lot going for it. It can't take in electrons. But can lithium give away electrons? Like gangbusters. It has a valence electron and it has virtually no attraction for it. So lithium is really good at giving away electrons. And if lithium gives away electrons, what is it doing to the other guy? Reducing it. And because it's really good at it, what does that make lithium? A strong reducing agent. Now, guys, you may bring this full circle in your brain because, guys, right now the most efficient not the most, but the most efficient batteries that we can build on an industrial scale are lithium-ion batteries, or even better, lithium polymer batteries. But, guys, lithium is a wonderful component of batteries because it's a beautiful source of electrons. It gives away electrons like gangbusters, so it's a great addition to any battery. All right, so guys, what do you think? Yeah, it's probably not. Is it on here? Where's it at? Oh, but notice that it's oh, I don't know. I don't even know if I could hypothesize a reason, because really it shouldn't be, right? Because cesium being larger would have an even lower electronegativity. I don't know. That's interesting. Well, it is the way it is, but I mean, everything's got to have an explanation, right? I don't know. I mean, obviously what that's telling us is that it's not just electronegativity that's the predictor of reduction potential. Reduction agent potential. But, you know, I don't have a good answer. I don't have even a bad answer for that. I don't know. It would be interesting to find out. I'm not sure. So guys, are you comfortable with the concepts? Here's the problem. I have absolutely no idea how they're going to hold you accountable for anything we just talked about if you don't get this on the test. Yeah, so I'd like to believe, well, I guess I don't know. I don't know. We don't have enough released exams out there for me to even postulate how they're going to hold you accountable for this. I'd like to believe that they're not just going to say fluorine has a reduction potential of 2.87 volts or whatever it is. Will it be a good oxidizing or reducing agent? They might. I don't know. Because it used to be, they loved to ask these questions because it caused you to interpret this chart and understand relationships. But taking away the chart takes away the opportunity to really appreciate the relationships. So again, guys, it's something that I know. Well, the book that tells us what's on the test says this is still on the test, but they took the chart away from you. So I don't know. But there you have it. Those are the concepts. So you guys okay? You're good? All right. So guys, what you're going to be asked to do with this in homework is simply you'll be given a list of elements and ions, and it will just ask you, is this a weak or strong oxidizing or reducing agent? And you'll just identify them given their position on the charts. Groovy? Okay. All right, so guys, we're done with that. You good? Okay, so now what we're going to do is we're going to relate voltage with spontaneity. We're frankly almost done for the day. We've already talked about it. So guys, I would encourage you to not write anything down till the very tippy bottom of this slide. Everything up until then is conversational. So here's where we're at. Up until now, guys, we understand that we can use batteries, we can use voltaic cells, as sources of electrical energy. Now guys, when we do this, and again, this was the thing that Jonathan was getting at, how do we know which one is the cathode and which one is the anode? And we answered the question by talking about the idea that this is a reduction potential chart, so the one that's higher on the chart will be the cathode. But if you screw that up, the bottom line is whenever we identify the cathode and the anode, we always do this in a way so that the voltage is positive, because that tells us that we've identified the anode and cathode properly. And remember the equation, guys, it goes cathode minus anode, right? Why do we go minus anode? Because it's actually an oxidation and not a reduction, so we have to flip the sign. Okay, so guys, here's the trick then. The idea then is that when we create these batteries and we pick sides and say the anode and cathode, we always do this in such a way so that they're written in the spontaneous direction. Voltage is positive. If we get it backwards, we just flip the terms and off we go. Well, guys, you need to understand that this whole idea of oxidation reduction reactions doesn't have to be limited just to voltaic cells. There are lots of other oxidation reduction reactions that we don't even think of as being batteries, but we still have an oxidation and a reduction taking place. So guys, in order to do this, what we can do is we can take our cell EMF equation and we can genericize it. So it goes like this. This is the equation that we use to figure out the voltage of a battery, right? Cathode minus anode. But guys, what happens at the cathode? What chemical process happens at the cathode? Reduction. And at the anode? Oxidation. So we can just rewrite it, and now we have a generic equation that allows us to study any electrochemical process. That you need to write down. Although, is it on the equation sheet? Hey, that's gone too. Okay, so guys, the question then becomes this. Now that we have a generic equation that is just the cathode, the reduction, minus the anode, the oxidation, so it's reduction minus oxidation, what values for this, and you know what, this should actually, well, it's not really E cell because it's not necessarily a cell, but guys, what values for this will indicate spontaneity? Positive values. So positive results to this equation tell us that it's spontaneous. Now, what if you get a negative answer? It's spontaneous in the other direction. Can you guys believe after today we only have one more day of new material, and that's Friday? Isn't that weird? You guys good? All of that making sense? Rather than cathode minus anode, we're just going reduction minus oxidation, and then it becomes generic. And if those values are positive, that means that it's spontaneous. Okay, so guys, let's make the link then with Gibbs free energy, and we're done. Again, don't write this down until we get to the bottom. So it goes like this. And we've already remembered this because we talked about it in the introduction. Remember, guys, that prior to what we're about to talk about, we only had one assured value that told us if a reaction was spontaneous, and that was delta G. If delta G is negative, it's spontaneous. If delta G is positive, it's spontaneous in the other direction. What if delta G was equal or zero? Equilibrium, right? Okay, so guys, again, negative delta G's indicated spontaneity. Well, now it turns out that voltage can also tell us if it's spontaneous, if it's an oxidation reduction reaction. So, as you might imagine, there's an equation that relates the two, and it's this. It's called the Nernst equation, and this you want to write down. So delta G is equal to negative NFE. So let's define the terms, and then we're done for the day. So guys, delta G is the change in free energy. You know that. And again, negative values for this indicate spontaneous. Positive values for this indicate spontaneous in the other direction. N is the tricky one. N is the number of moles of electrons exchanged in the process. Then guys, F is what is called Faraday's constant. Maybe this is what you were referring to, Taylor. The quantity of electrical charge in a mole of electrons? No, because you were thinking voltage. And then guys, E is of course the voltage of the cell. Yes, for this it is. So guys, as you've got this down, I would encourage you to not write down that last bullet point. Let's just talk about it. So this is the idea. You ready? Follow along. 30 seconds, we're done. What delta G values are spontaneous? Negative. What E values or what voltages are spontaneous? Positive. Now, notice that N, the number of moles, has to be positive. It's a number of moles. Faraday's constant, which is a constant and it's on the equation sheet, is also positive. So guys, the idea is this. So there's a negative sign hanging right here. So if this is positive and this is positive, what if E is positive? Positive, positive, positive. If E is positive, what does that make delta G? Negative because of this, right? So our concepts line up. A positive E, given that these two are always positive and there's a hanging negative sign, if voltage is positive, delta G is negative, both of those indicate spontaneity. And then similarly, if our voltage is negative, that makes the result of the right-hand side of the equation positive. Delta G is positive, indicating it's non-spontaneous. So our concepts line up relative to spontaneous and non-spontaneous because, again, positive voltages will result in negative delta G values because N and F are both positive and there's a negative sign there. You got the idea? Okay, so guys, we are done. So here's your homework.